Hey everyone! So we're going to take a look at something called the chain rule for antiderivatives right now. And the shorthand notation of this is to call it U substitution. When we were talking about derivatives back in semester 1, we had our original derivative rules that we could apply, but then when we started getting into composition functions, we had to do something called the chain rule, and that was where we were talking about peeling the layers of the derivative functions themselves. For example, if you take a look at the square root of 5x plus 7, that's a composition. You are taking 5x plus 7 as a function and you are raising that to a 1/2 power. So the same idea holds true when you're finding antiderivatives. If you can't apply one of our antiderivative rules, you can try something called U substitution. Our old derivative rules can be applied in reverse, and as long as you remember the derivatives and integrals are inverses of one another, a lot of students can puzzle these out. Now, I was never that student. I had to have a process and a rule and a way of doing things. So either way, take a look at this first antiderivative. If you are asked to find the cosine, the antiderivative or the indefinite integral of the cosine of 3x dx, okay, a lot of students would maybe guess that the antiderivative is the sine of 3x. Okay, so if you take a look at that and you guess, maybe it's the sine of 3x. But remember, I said that one of the ways you can check your answer is to take the derivative of that and see if you come back at the original integrand. Okay, so if you take the derivative of this, you're going to get the derivative of the sine of something is the cosine of that thing, but then you have to multiply by the derivative of the inside. There's the chain rule for the derivative. Right, so you're multiplying by 3. And then the derivative of that constant is just 0, so it goes away. Okay, so this almost looks like our original integrand, but not quite. So there's a little bit of a problem here. Now, U substitution can be used to help you anytime you have a composition function. And just like when we first learned about compositions with derivatives, you're going to do the same technique where you're going to substitute U in for a function of x. Okay, so let's take a look at that cosine of 3x again. Now this is a pretty simple U substitution problem, so it's going to seem like more work than necessary to do this, but hang with me here and we'll see how this can be useful on more difficult integral problems. So the first thing that I'm going to do is I'm going to say let's let U equal 3x. Okay, so I'm just going to do a substitution here. That would make my indefinite integral turn into the cosine of U, but then we've got a problem. It says dx, okay? And the idea is you want to make sure that your variables match up. So I want to somehow get rid of this dx, okay, and substitute it out. So let's go back to our original substitution equation, and let's just go ahead and take the differential or the derivative of both sides. I'm going to show both techniques, whether you just take the derivative or the differential, and we'll talk about that in class. So I'm just going to do the derivative because it seems to be what everyone is most comfortable with. Okay, we'll say du dx equals 3, the derivative of both sides. Okay, and then again, we're trying to get rid of dx. So if you let du equal 3 dx, then that means that dx equals 1/3 du. I just divided that 3 over to the other side. So this is a straight substitution then because I'm trying to get rid of dx and I have something that stands for dx. Okay, so now I can go ahead and substitute that in and we'll have the cosine of u, but instead of writing dx, I'm going to write times 1/3 du. Now I have only u variables, and this is all multiplication, so I can pull out that constant multiple. And you ask yourself, do I know a function that when I take the derivative of it, I would end up with the cosine of u? And the answer to that is the sine of u. And don't forget the plus c. And then the last step, you are going to go back up to where you said what u stood for, and you're going to plug that right back in for u. Okay, the original integrand was in terms of x's, so we have to have an antiderivative in terms of x's. So this is going to be 1/3 times the sine of 3x plus c. And that is the antiderivative for the cosine of 3x. And you can double check it by taking the derivative. Hands down, the most challenging part of U substitutions is deciding what a good U is going to be for the problem. So you just have to, at first, just kind of, I'm going to give you recommendations at the beginning, and then once you start to get the hang of it, you'll see what you should pick for your U. But the idea is you always want to pick a U whose derivative is also in the integrand. Okay? And I'm going to start you off. We're going to write out this original integrand. Instead of using a radical, we're going to use an exponent of 1/2. And right now, I'm going to let you try this one. Even though I've only done one example problem, I'm going to let you try. I'm going to tell you that you're going to let U equal 3x plus 5. Okay? So I want you to press pause and find the derivative of U and substitute things in and try to get this integrand so that it's in terms of only U. Then take an antiderivative and plug back in. Okay? So press pause now. All right, let's see how you did. First things first, let's go ahead and rewrite our original integrand. And instead of writing 3x plus 5, I'm going to say U to the 1/2. But I have got a dx and a U, and x's and u's don't play nice together. Actually, x's don't play nice with anybody. See what I did there? Okay, so if you take the derivative, you'll have du dx equals 3. And remember, you are trying to eliminate this dx over here. Okay, we want to get rid of it. So that means we're going to need to solve for it in something else, in some other equation. And we've got a nice little equation over here. So I'm sorry that the numbers ended up being the exact same as the previous page, but it's going to be 1/3 du equals dx. Okay, so I've got an x by itself, and I can do a straight substitution now. And the problem is going to read U to the 1/2. Instead of writing a dx, I'm going to write 1/3 du. Are the parentheses necessary? No. You can take them out because it's all multiplication. And again, we've got that constant multiple of the 1/3 out to the front. So we've got U to the 1/2 du. And now I've got an integrand only in terms of U. I've pulled out a constant, and we can go ahead and find the antiderivative for this guy. Now we're going to use the power rule. Do you remember what it is? All right, we're going to raise the power by 1. And we would divide by the new power, but if you divide by the new power of 3/2, you're technically multiplying by 2/3. Okay? And you would have the plus c at the end. Don't forget the plus c, everybody. This is going to end up being 2/9. And don't forget now, I say that too much, I'm so sorry. We've got U to the 3/2, but instead of writing U, we're going to substitute back in what U stood for. What do U stand for? U stand for 3x plus 5. I'm here all night. No, really. So 3x plus 5, all to the 3/2 power, plus c. And you can, again, I strongly recommend checking your answers by doing the derivatives because you're going to get that practice that you need of going forwards with derivatives and backwards with the antiderivatives. And the more fluid you get with the process, the better off you're going to be for the AP exam and for my quizzes. All right, let's go ahead and move on to number 2. I'm going to tell you what U should be. Here we've got 2x cubed minus 1 to the 4th power and then times x squared. And typically, a rule of thumb is that you're going to let U be represented by a function that is either raised to a higher power or the cosine or a trig function is being taken of it. And in this case, we've got something being raised to the 4th power. So we're going to say, let's let U equal 2x cubed minus 1. Okay, so press pause, give this problem a try all on your own, and then come on back. All right, let's see how you did there. You like that? It's very funny. All right, we're going to let the motorcycle hang out up there. I really miss summertime. I don't know about you guys, but this is ridiculous weather. we are going to take the derivative of this. Oh, actually, let me go back over here and do the substitution. You will have u to the fourth times x squared dx. Now, here's a little trick on this guy. There's more than just a dx. I need to get rid of everything that has an x involved in it. So x squared dx is what I'm aiming for. That's what I'm trying to get rid of. So if you go back over to your derivative again, you've got du dx equals, and then derivative of the right-hand side is going to be 6x squared. And if you multiply the dx over to the other side, you'll have 6x squared dx. Now we're almost there. Take a look. I've got x squared dx in the problem, so that's really good. What I don't have in the original integrand is I don't have that 6 that this derivative piece has, just x squared dx. So what I'm going to do now is I'm going to divide over the 6 and make it 1/6 du. So again, now I've isolated the part that's also in the integrand that has x's involved with it. And if we do a substitution now, you're going to have u to the fourth. And instead of writing x squared dx, we can write 1/6 du. It won't always turn out that you have a constant in front. So, you know, that's not a rule or anything like that. But now we've got our integrand in terms of u, and now you can go ahead. Don't forget to take the antiderivative. That's a really common mistake, is you get this far and then you're like, oh, I'm done, and you substitute back in. But take an antiderivative, and you're going to use your power rule for this one. So u to the fourth, you're going to raise the power by 1 and divide by the new power. And don't forget to add your c. And substitute. Never goes away, everybody. Substitute that u back in so that you get your original variable of x back into the problem. So this is going to be, instead of saying 1/6, I'm going to combine the 6 in the denominator here with the 5 in the denominator here, multiply those out and get 30. And instead of u, we'll have 2x to the third minus 1. All of that is raised to the fifth plus c. La 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 la. Right? All right. One more page. Hang in there. Okay, this is where I get really sneaky because there's 2 more problems left and I'm trying to keep my video short. So I'm going to have you press pause and do these 2 problems on your own. I even tell you what the u should be. And my only hint for you is on number 4, rewrite it so that the squared is not located where it's located. We did derivative problems like this where we would rewrite the square to the outside. So instead of cosine squared of 4x, rewrite that as cosine of 4x quantity squared. Okay, so I'm going to press pause, and just like magic, in about 5 seconds, you're going to have all the work up and you're going to be able to check your work. So 5 seconds starting now. Ta-da! Okay, how'd you do? Hopefully you got it right, and if you didn't, look through my work right now, press pause because I'm going to go on and I'm going to show you the answer for the next one in 5 seconds. But if you get stuck or you're not sure, make a note in the margin and make sure you ask me in class. So you've got 5 seconds until I show you the answer for number 4. 5, 4, 3, 2, 1. Ta-da! All right, so take a look at this one, and again, look through each part of the problem. I'm hoping that this lesson was fairly straightforward. This is a really challenging subject, so if you get a little confused or you're stuck, stick with it. I remember it took me a couple of times working with U Substitution when I was in high school, so if you don't get it right away, don't get frustrated. If you do get it right away, be patient with those that don't and help them out in class, okay? Hope you guys have a good night, and I will see you next time. Bye.